go on. So this is the lecture 15 of the course Climate Data Science. We will do a recap on graph neural networks today. So that's what we were doing in the last class, and so we didn't have classes from 1st to 10th because I was having my PhD defense. And okay, so just like any other machine learning paradigm, graph neural networks is the new frontiers of machine learning. Now in graph neural networks, you basically have a graph in and a graph out. So what do we mean by that? So first of all, we have to understand what are graphs. So graphs are composed of vertex or nodes. We have the links and we have the entire graph. Okay. Now each node or vertex is represented by an embedding. Each link is also represented by an embedding, which is called the edge embedding. And then we have a global or a master embedding. There can be two types of edges, an undirected edge and a directed edge. So in a directed edge, we have a parent and a child node. So you can represent different data types as graphs. First example that we can think of is images. So in the images, each pixel here, we can interpret it as a node in the graph. Okay. Now each pixel is connected. So for example, this pixel number 20 is connected to so we say that it's connected to all the neighboring pixels, right? So 10, 11, 21, 31, 30. And you can see that the connections here are represented by the lines or the edges, what we call as edges. Each graph can be represented by an adjacency matrix. Now, in this case, adjacency matrix, so on the x-axis and on the y-axis, both the axes have all the nodes, and it's a matrix consisting of zeros and ones. You have a one wherever you have a link, right? And on the right, extreme right side is the graphical representation of the image data set. Now you
Sir?
can also, yeah.
Sir, screen is not shared.
Can others see my
Yes,
screen?
yes,
Sir, we
yes.
can see.
Yes, sir.
Maybe can you refresh
Yes,
or
okay, sir.
try join again?
Okay, sir.
Okay. Yeah.
Yes.
So then we have text as graph. So for example, this sentence, graphs are all around us. Now this, so each word is a node, and we are having directed edges or links between the different nodes. So you can see that so this word R, it is connected. So graph is a parent and it is connected to R, and then R is connected to all, and then all is connected to around. So there is a structure in it. So if these were undirected edges, so this also, so we would be having this also would be blue. So wherever it is blue, it is 1. Rest of the places it is 0. Then you can have, so these are the examples of structured data on graphs. We can also have unstructured data on the graph. For example, this is a representation of a molecule in chemistry, and so this is a caffeine molecule. So you can see that the adjacency matrix is unstructured. There are different types of data that can be represented as graphs. For example, social networks, then citation networks, and there are other examples. So there are different types of tasks that can be solved by using graph neural networks. So one is the graph level task. So in graph level task, the job is to basically predict for the entire graph a particular property. For example, in this case, we have the two classes as red and gray. So we given structure of the molecule or a structure of the this chemical compound, we are given the task of predicting something like whether the graph contains two rings or not. So we make this into a supervised learning problem with the inputs and the labels, and then solve it as a graph level task. Then we can have a node level task. In a node level task, let's say we have to classify the nodes. So these are two people, and these are the teams that they have made. So and each person is represented by a node. So you can see that herein you have to predict the node properties, and then you can have an edge level task. So in an edge level task, our job is to predict the edges in the graph. So we have, so you can have this example in which we have this as an image, and in this image, so you first pass it through a segmentation algorithm. Now say the image segmentation algorithm gives you the different objects. So these are the different objects: Johnny, Daniel, referee, Matt, audience. And then you so you can formulate this as a graph problem wherein you have to predict the links between the different nodes. So this is the edge level task. Okay, so there are some challenges of using graphs in machine learning. The first challenge is that by using adjacency matrices, so for example, this is the adjacency. For example, this is the graph that we have. Okay, and just take some represent. Yeah. Okay. Yeah. So this is the graph we have. Now, these are the connections in the graph. Now, just by changing the order of the nodes in the adjacency matrix, you can see that your adjacency matrix changes, right? So it's not permutation invariant, and that is, so for the same graph you can have all these different types of permutation matrices depending upon what are the order of nodes that you keep in the graph. For example, a b c d, a b d c, a c b d. So for different orders of the nodes you can have different types of graphs. So to overcome this difficulty, we come up with the concept of adjacency list. Now, so in an adjacency list, what we do is, what they do is they describe the connectivity of edge ek between nodes ni and nj as a tuple I comma j in the kth entry of the adjacency list. So let's say this is the kth entry, k is equal to 1 here. So this is represent the connectivity of the edge ek, that is edge e0, or like if in Python e0, and this is the, let's say, 0th entry representing the connection between node 1 and node 0. Okay, so here you can see this is representing the connection between node 2 and node 0, node 4 and node 3, 6 and 2. So rather than having the adjacency matrix, we come up with the notation of adjacency list. And it should be noted that the figure uses, okay, so instead of node tensor of size n nodes, we will now be dealing with node tensor of size n nodes by node dimension. So each node will be represented by an embedding. So you have to embed the so as we saw in the beginning of this blog, that each node and link and the entire graph, it will be represented as an embedding vector, right? So then, so a graph neural network, seeing the definition, is an optimizable transformation on all attributes of the graph, nodes, edges, global context, that preserves the graph symmetry. So it should be permutation invariant, and we are going to build the GNNs using message parsing neural network framework proposed by Gilmer et al. Using the GraphNets architecture similar to Battaglia et al. So graph neural networks adopt a graph in and a graph out architecture, meaning that these model types accept a graph as input with information loaded into its nodes, edges, and global context. So this is a very important thing you have to remember, that in a graph neural network you will have a graph in and a graph out, and we won't be changing the connectivity structure in the graph. Okay, and so progressively transform these embeddings without changing the connectivity of the input graph. So every node and so depends upon the kind of information we have. Ideally, the nodes and the edges and the global context will be having the embedding information. Now those embeddings are the weights that we are learning from this graph machine learning, and those embeddings are something that we are learning without changing the connectivity structure in the of the input graph. So we are not changing the connectivity structure of the input graph. Now, as a simplest graph neural network, so we can see that there are three different types of transformations that are required to be done, or like that can be done. I should not say that are required to be done. So let's say this is the graph, the connectivity structure that you maybe know from the domain knowledge, and this is the transformation. So this is the embedding for the global context. This is embedding for the different vertices or the edges or the links, and no, this is for the edges and this is for the vertices for the nodes. So we can see that just like in a any other machine learning problem, we have to find out this mapping function f, which maps from un to un plus 1. So this is the layer n plus 1, and we have to, so you can do it as a graph level task, node level task, or as an edge level task. And then, as is common with neural networks, modules or layers, we can stack these graph neural networks layers together. Now, because a GNN does not update the connectivity of the input graph, we can describe the output graph of a GNN with the same adjacency list. So the adjacency list of this output graph doesn't change. It is same as the adjacency list of the input graph, and the same number of feature vectors as input graph. So the number of feature vectors also remain the same. But the output graph has updated embeddings since the GNN has updated each of the node, edge, and global context representation. So the embeddings of the nodes, the edges, and the global context, they are something that we are trying to update. So now the thing is that we might not always have information on the nodes, or we might have information on the nodes but not about the edges. So let's say we consider the problem of binary classification, and you have to do the classification of the nodes, right? And the graph already contains the node information. So the approach is straightforward. For each node embedding, apply a linear classifier. So you have the information on the nodes, and you want to do so you have the label data set in a supervised learning problem. You have the node embeddings and you have the labels. So red and green are our we are doing a binary classification problem, and we have to find out this classifier C, which is the mapping function. However, it is not always so simple. For instance, you might have information in the graph stored in the edges, but no information in the nodes. But you still need to make prediction on the nodes. So you might not have any kind of data about the nodes, but let's say you have the information about the edges, and we need a way to collect information from edges and give them to the nodes for prediction. So we can do this by pooling. Pooling proceeds in two steps. So for each item to be pooled, gather each of their embeddings and concatenate them into a matrix. And then the gathered embeddings are then aggregated using usually using a sum operation. You can use another different aggregator as well, like you can use max or you can use min. So for example, we do not have the data at the nodes, but we have the embeddings of the edges or links. So let's say we want to generate the embedding of this node, right? So what we'll do, we will basically aggregate all the links, all the edges which are connected through to this node. So these are embedding vectors for all the edges which are connected to this node. So we then aggregate it using a function. So let's say sum. So you just sum all of them, and then this is the aggregate information from the adjacent edges. So this becomes the embedding for this node. So similarly for this node, so this is the embedding. So you can see that you can pull in the information and generate embeddings for the nodes. If you want to do the transformation on nodes and the information is not available on nodes, you can do a vice versa uh, thing also for the edges. If you have information on the nodes and your information on the edges is missing. So if we only have edge level features and are trying to predict binary node information, we can use pooling to route or pass information to where it needs to go. And the model looks something like this. And if we only have node level features and are trying to predict binary edge level information, so in this case, you only have node level features, and now you are trying to do binary classification on the edges, right? On how the different nodes are linked to each other. So in that case, you would perform pooling from nodes to edges. So you can see here, this is the pooling that is being performed from nodes to the edges. And if we only have node level features, we need to predict a binary global property. So we need to gather all the available node information together and aggregate them. So if you have only node level features and you want to predict something for the entire graph, you need to collect information from all the nodes. And this is similar to global average pooling in CNNs. So the same can be done for edges. For example, if you have the information from the edges and you want to predict only from edges and you want to predict something for the entire graph, so then you will accumulate or pool in information from all the edges. So in our example, so classification model C can easily be replaced with any differentiable model or adapted to multi-class classification using generalized linear model. So you can see that you have an input graph, you have the graph neural network blocks, you have a transform graph. So by transform graph, what we mean is that the connectivity structure is remaining the same, but you can see that the embeddings are changing. And then you have a classification layer and we are doing a prediction, which can be node edge or global prediction. So we have now demonstrated that we can build a simple GNN model and make binary predictions by routing information between different parts of the graph. This pooling technique will serve as a building block for constructing more sophisticated GNN models. If we have new graph attributes, we just have to define how to pass information from one attribute to the another. And note that this simplest GNN formulation, in the simplest GNN formulation, we are not using the connectivity of the graph at all inside the GNN layer, and each node is processed independently, as is each edge as well as the global context. We only use connectivity when pooling information for prediction. So this is a very important thing to remember. Connectivity is not changed. You only use connectivity when you have to pool the information for prediction. And now, so when you have to pull in the embedding from different nodes or different the edges or links, how you will do that is by passing messages between the parts of the graph. So we could make more sophisticated predictions by using pooling with a GNN layer in order to make our learned embeddings aware of the graph connectivity. So we can do this using message passing, where neighbors, nodes, or edges exchange information and influence each other's updated embedding. So message passing works in 3 steps. So for each node in the graph, gather all the neighboring node embeddings, which is the G function described above. Aggregate all the messages in an aggregate function like sum. You can also use max or min. All pooled messages are passed through the update function. So the update function is this one, sum, min, or max, usually a learned neural network. And just as pooling can be applied to either nodes or edges, message passing can occur between either nodes or edges. So, and these steps are key for leveraging the connectivity of graph. So you can see this, and yeah. So there are different methods for uh, for doing this. So uh, for performing the passing the information from the nodes to edges, edges to nodes. So you can have this as a this kind of a message passing layer. So wherein you are passing from vertex to edges and back there. One of the message passing which is very popular is known as the weave layer. So in weave layer, you are passing the information from the edge to the vertex, vertex to the edge, and then back from the edge to vertex and vertex to the edge. So this forms a complete like it's like a coupled message passing, and it's we'll see in the coming sections that what is the importance of message passing in the graph neural networks. So we can also have a global context. So we can so basically what would happen is that after a particular number of layers, the this node, for example, will start receiving information from the nodes which are farther away from it. But if it is a big graph, then in that case, two nodes which are far away from each other won't be able to exchange information and in any way because of the distance within the graph. So for that, we make something known as that as the global representation of a graph, also sometimes called as the master node or the context vector. So with the global representation or the master node or the context vector, the information is it's like a master node, and information is exchanged between all the nodes of the graph with each other. So then this is a GNN playground that they have shown here. So for example, if we have this chemical compound, and we have to predict whether it is pungent or not. Now ground truth says that it is not pungent, and these here represent the different types of chemical compounds. I'll show you how they are different. So we can in this playground we can change the depth, so we can increase the number of layers of the graph neural network. We can say now see now model is predicting that it is 14% pungent, and it is now okay. So this changed to 18% pungent, and this is the node embedding size. So node embedding size is 50, edge embedding sizes you have options from 5, 10, 20, and this is the global embedding size. So the ground truth says non-pungent, anything less than 50% is non-pungent, greater than 50%, let's say we classify as pungent. So this is okay. You can also change the type of molecule. So here you can see that the blue color represents nitrogen, and you can change the bond as well. So we have changed this bond to a double bond. So it says its ground truth is unknown. We don't have this information in the ground truth. Okay. So these are the different compounds, and you can see what the model is predicting and what is the ground truth. And then we have some empirical graph neural network design lessons. So for example, number of parameters versus performance. So on x-axis we have the number of parameters, on y-axis we have the test area under the curve, so whether it is pungent or not. And this area under the curve, it is you can see that it is coming highest for like, it's not like we need a large number of parameters. So even for a small number of parameters, somewhere around 3000, you can see that we are getting the area under the curve somewhere around 0.8 to 0.9. So Surprisingly, a higher number of parameters does not correlate with high performance. Graph neural networks are very efficient, a parameter efficient model type for even a small number of parameters, that is 3000. And we can already find models with high performance. Next, we look at the distributions of the performance of aggregated based on the dimensionality of the learned representation of different graph attributes. So this is the node dimension. So you can see that as the as the embedding dimension of the nodes is increasing, the performance of the model is increasing. Similarly, for by increasing the edge dimension and the global dimension, embedding dimension, the performance of the model is improving. And we can notice that the models with high dimensionality tend to have better mean and lower bound performance, but the same trend is not found for the maximum. So some of the top performing models can be found for smaller dimensions. So but like for the maximum, this is fine for the mean performance, but the maximum performance, you can see here we are getting at node dimension equal to 25, which is higher than the maximum performance of the node dimension, which is equal to 50. And then this is the next we see the breakdown of performance based on the number of GNN layers. So here we are seeing that 1, 2, 3, and 4 layers at these different number of layers. What is the model performance? You can see here this model is standing out. So this model is having, this is blue color. So blue is this one. It is having 2 layers. So the box plot shows similar trend while mean performance tends to increase with the number of layers. The best performing models do not have 3 or 4 layers, but 2. And does our dataset have a preferred aggregation operation? So we can see that the aggregation so these are the different aggregation operations while pooling some max or mean. So here the best performance is shown by the sum operator. So we can see that and also architectures colored by the style of message passing. So what is the style of message passing you should have? So nodes, and so if you are passing messages only between edges is this color, if only passing between nodes. So you can see that, so this color, this bar plot is the nodes and edges and globals. So overall you see that the more the graph attributes are communicating, the better the performance of the average model. And our task is centered on global representations. So explicitly learning this attribute also tends to improve the performance. So that's all about yeah. So this block. So we can also have different other types of graphs known as multi-graphs, hypergraphs, hypernodes, hierarchical graphs. So on the left side we have a multi-graph. So in the multi-graph you can see that these are like 2 graphs which are connected to each other with 3 edge types. So what are the 3 edge types? You have, one is blue, another is red, and then you have the green. And on the right we have a 3-level hierarchical graph. So in this one you have this graph 1, graph 2, and graph 3. So they are connected to these hypernodes, which are then connected to this global nodes. And so we can also have something known as inductive bias in the which can be useful for improving the performance. Now what is inductive bias? So when building a model to solve a problem on a specific kind of data, we want to specialize our models to leverage the characteristics of that data. So for example, the different characteristics can be the image data or the time series data or the text data. And when this is done successfully, we often see better predictive performance, lower training time, fewer parameters, and better generalization. So when labeling on images, for example, we want to take advantage of the fact that dog is still a dog, whether it is in the top left or bottom right corner of an image. Thus, most image models use convolutions, which are translation invariant. So For text, the order of the tokens is highly important. So recurrent neural network process data sequentially. Further, the presence of one token can affect the meaning of the rest of the sentence. And so we need components that can attend to other parts of the text. So which transformer models like BERT, GPT-3 can do. So these are some examples of inductive biases. So inductive biases are basically biases that are that you either introduce in the data or which are there in the data. So for the image data set or for the sequential data set, there is a specific sequence, and there are these dedicated models which are which basically take care of these inductive biases, and where we are identifying the symmetries or irregularities in the data and adding the modeling components that take advantage of these properties. So in case of graphs, we care about how each graph component, edge, node, or global is related to each other. So we seek models that have relational inductive bias. And a model should preserve the explicit relationship between the entities, which are reflected in the adjacency matrix, and preserve graph symmetries. So that's all about the inductive biases. These are the different types of aggregation operators that you can use. And then we have something known as the graph convolution networks and graph attention networks. I think you can go through these on your own. We will see graph convolutions in detail. So this is the we have now finished the introduction to graph neural networks, and then I'll quickly go through understanding convolutions on graphs. So maybe you can go through this. What is the time? 2:47. So it's there in the slide, and this is basically a peer-reviewed blog, and they have taken a lot of effort to make this. You can see here, these are the 3 reviewers who have reviewed this, and you can go through this second blog to understand the convolution, to understand the convolutions on graphs. So we will move to the next section now. So the next thing that we will do is, so quickly I will go through the basics of deep unsupervised learning. So yeah. So this is a course which is being taught at UC Berkeley, and the entire course, it says 12 lectures. These are around 2.5 hours each, and all are available on YouTube. So I will quickly go through the basics of deep unsupervised learning. Okay. So what is deep unsupervised learning? It's capturing rich patterns in raw data with deep networks in a label-free way. So let's say you don't have labels in the data. It's an unsupervised learning problem, and you are given the task of modeling the data, or you have to perform unsupervised learning. So you do not have any labels, you do not have any y values. So in a dogs and cats image data set, you have the labels as dogs or labels as cats. So for example, consider the scenario where you do not have any such labels. So the models that we would use are generative models, which would be used to recreate raw data distribution, and another way is self-supervised learning. So why would we care? So Geoffrey Hinton gave this very popular statement in 2014. He says that the brain has around 10 to the power 14 synapses. So synapses you can understand as the links between the neural networks, and will live only for about 10 to the power 9 seconds. So we have a lot more parameters than the data that we can measure, and this motivates the idea that we must do a lot of unsupervised learning, since the perceptual input is the only place we can get 10 to the power 5 dimensions of constraint per second. So Jan LeCun, who and these are, so Geoffrey Hinton is known as the father of deep learning. Geoffrey Hinton, Jan LeCun, and another person, Yoshua Bengio, they won the Turing Award some years back for their contributions to bringing out deep learning, which has led to all the revolution in AI and machine learning. So Jan LeCun said that if reinforcement learning is the cherry, supervised learning is the icing on the cake, unsupervised learning is actually the cake. So that's the importance of unsupervised learning. And what we are trying to find out is ultimately is ideal intelligence. That is, we're trying to compress the knowledge in and making optimal action making agent. So AI. So you must have heard about terminologies like trustworthy AI and explainable AI. So those are the directions where the community is going right now. And so there are a lot of powerful applications there which are in use today, uh, which come under the purview of deep unsupervised learning. The most popular of them is, so this is from 2020, and Google must have updated its search, I think, to GPT-3, or maybe there was a new model which came out, DAL E2. So no, so DAL E2 was from OpenAI, but Google also came up with a new model which was able to do a lot of stuff. And so but by until 2020, so Google search was being powered by BERT. So we have we have seen, or we have had a couple of classes on natural language processing. So you can go back to revise that, or if you others who remember, then you can generate novel data. You can do stuff like audio. You can analyze or do audio prediction using WaveNet. You can use pix to pix, which is a image to image regression algorithm using generative adversarial networks. So these are the state of the art algorithms, and you can see that in 2006 this was the state of the art. So deep belief nets, uh, these were the kind of realistic images that we could generate, and by 2013 we could generate something like this, and this is in 2014. So you can see that these are still not very good. This is in 2015. So this is using the generative adversarial networks. Uh, these are the images which are generated by the model and which were not fed into the model. And this is in again in 2015. So you can see that the human faces, that these are the images of people who have never existed. So this is out of the sample data generation. You can do things like this problem is super resolution, image super resolution. So if you have a low resolution input image and you are given the task of improving the resolution of that image, which is very similar to what is downscaling in our climate data science application. So this is the model output from the model SR ResNet. This is from SR Gan, and this is the original. So you can see that, like, visually, SR Gan and original, it's very difficult to identify, like, whether SR Gan is not the true image or not, right? So then you can do different things like you can you can use cycle GANs to do image style transfer. So I don't know if I've shown this in the class. So style. transfer. So you can yeah, dpart.io. Yeah, so there is this website deepart.io, using which what you can do is, oh, it's not working. Yeah, anyways, I think it's not working now. So you can apply a style to an image, again using GANs. This is also generated using a GAN, and then you can generate audio by using WaveNet. So this is very similar to the time series prediction or time series forecasting algorithm. So for example, this yeah, this won't be, can't hear that. And then there are examples of generating text. So for example, I recently saw this GPT-3 text. So you can see this that let's say I just pass this through the model, and the model is generating this coherent looking text. So I just gave the text generation API is backed by large scale unsupervised language model that can generate. So now the model is generating it's just completing and it's generating this text on its own, so as to not need the additional validation. These algorithms can be adapted to different problems such as, so this was like some years ago, this was really great when people saw that models, such NLP models can be as good as humans. Not all the examples that they generated were realistic, but at least generating some examples was also a big feat. So models can also generate math. So for example, you pass on this LaTeX code to a to an NLP model, and without using LaTeX, it just generates this math. And so this is the generate text that we have already seen, but this is dangerous also sometimes. Like if you say recycling is good for the world, no, you could not be more wrong. The model is saying the recycling is not good for the world, bad for the environment. So, but still, it's generating some coherent. And this is GPT-2, and this was in 2019. After that, GPT-3 and a lot of other models have come, which are state of the art. So yeah, this was the website. Talk to transformer.com, and let's say we try an example. So model, so while not normally known melon space. So this is something which is generated by the model. You can increase the number of characters to generate, and this will just, so this is this model is like an RNN which has to generate the next word conditional on the all the pre words that come before it. So this is like conditional generation. And there are other examples like compression. So you have, there are two types of compression: lossless compression and lossy compression. And then we have the BERT revolution. So there is there is this benchmark, glue benchmark leaderboard we can see. So different groups, they would publish their models on the open source data sets. This is taking time to load. So but you can see that and they would be judged like on the test data which is not available to them. So you can see that there are these different teams which are competing with each other. And then in computer vision problems, there is something known as contrastive learning, which is which is so which is the state of the art, and it can help you in improving the accuracy of your models. So this is the summary of the introduction to deep unsupervised learning. There are a couple of more concepts like autoregressive models. So this is from the lecture 2. You can go and see this entire series at your end on deep unsupervised learning. So there are models like pixel RNN and pixel CNN, and these models are slightly so okay. We'll first maybe go through Gan. So there is this Gan specialization. It's a 3-course specialization by deeplearning.ai on Coursera. Okay, so course 1, 2, and 3, and we will see the slides from the course 1 today. Okay, so these slides are from deeplearning.ai, and this is the week 1 so of generative models. So what are generative models and what are their different types? So first we'll see the difference between generative and discriminative models. So in discriminative models, you have to basically make a model. You have to make a classifier which is, let's say, it's differentiating between cats and dogs. Whereas in generative models, you give a noise and you give a class, and then your task is to basically generate the features. By features, what we mean is that we have to generate the data itself. So here, from the features, from the images, we are trying to predict the class. Whereas here, given some noise and a particular class, let's say if I ask the model to generate an image of a dog, and if I give a noise as 0.6, so it should generate the image of dog. So if I want the different lots of images of dogs, so that's what generative model will do for me. And then so these are the different images. For example, you give different noise and you give the class corresponding to the dog, and different images of the dog the model will give you. Now a fundamental type of generative models is variational autoencoders. So in an autoencoder, we basically have an encoder and a decoder. So in an encoder is basically it takes
Hello, you are muted.
yeah, sorry for that. So we basically have an encoder and a decoder. So and you have a latent space. So it's like you have an image in and an image out, and you can do different things with the autoencoders. And variational autoencoders, you also have something like it's being modeled by the mean and standard deviation. So you also have other numbers which are going on from here. So let's say you train a variational autoencoder and you have a latent space in between. Now if you sample a number from the latent space and you pass it on to the decoder will give you this image. So in this autoencoder is nothing but it's a neural network in which the input and output remain the same. So you pass an image as an input and you get an image as an output. So for example, you have trained it with a lot of images of dogs, cats, different classes. So you take a sample from the latent space and you pass it to the decoder, and the decoder gives you this the image of the dog. And autoencoder is also a type of a generative model. Now, what are generative adversarial networks? So in the generative adversarial networks, you basically have a generator and you have a discriminator. Now generator and discriminator, they compete with each other. So now once they compete with each other, so generator is trying to fool the discriminator and discriminator is trying to fool the generator. After a point of time, the generator becomes so good that the discriminator, so the job of the discriminator is to identify that whatever image. So let's say the generator is like an autoencoder, it is, or it is generating an image, and it is being passed to the discriminator, and the job of the discriminator is to identify whether that image is a fake image or a true image. So the discriminator, once the generator becomes so good that it is generating a fake image, but discriminator is not able to identify that it is generator is generating a fake image, and it says that okay, oh, this is coming from the actual original distribution. That is the point where we say that the GAN has trained, and maybe we would train it somewhat further also, and then we just throw away the discriminator and we just have the generator. So generator actually is a very good image generator in that case. So these are generative adversarial networks. And so generative models learn to produce examples. Discriminative model distinguish between classes. And some examples of real life GANs, so cool application of GANs and major companies using them. So okay, this is Ian Goodfellow, and I hope that all of you know him. He recently, because Apple uh, changed its policy to in-person office, he's the inventor of GANs, and he was I think lead AI scientist at Apple, and he has resigned now. It was a big news. So he tweeted this image showing the evolution of GANs. So from 2014 to 2018, this is a image generated by GAN, and this person is not real. I will just show you. This person does not exist.com. So you can see that this person has never existed. Like, I mean, it's not a real person, but uh, it's you can it's difficult to identify. Like, if you just get this image or you show this image to somebody, people can't tell whether these people are not real or these people have never existed. So these are images which are generated by GANs. So at the back end, GAN is running, and so you can go here and see the algorithm. So yeah, this is style GAN. Yeah, where were we? Yeah. So then these people do not exist. So these people are not real. And there is a very popular Barack Obama fake GAN. Yeah. So you can go to YouTube and search for this. So this will take some time. Okay. There is a video of Barack Obama who is giving an introduction to an MIT class, teaching on AI, and he's just speaking something and which is fake. So GANs can be used for image translation from one domain to the other. So this is known as cycle GAN. This can be very useful for our applications because uh, you can give an input of maybe different variables and get an output of the variable of interest, and this will train really well. So then we have something known as GANs, cycle GANs, and yeah, he's saying that GANs are magic because GAN is basically generating something which is which you have which it has not seen. The data is not there in the training data itself. And then there are you can generate 3D images, 3D designs using GANs. These are the companies using GANs. Super resolution is also a very big example of GAN. And so intuition behind GAN. So the goal of the generator and discriminator and the competition between them. So generator learns to make fakes that look real, and discriminator learns to distinguish real from fake. So and so this is what is happening, and yeah. So generator, it's like initially it would generate outputs which look really bad, and with discriminator will quickly pick up and will identify as fake images. But as you train more, the generator will start making uh, images which are more realistic and good enough that the discriminator then is finds it very difficult to identify them as real or fake. Okay. Yeah. So generator's goal is to fool the discriminator. Discriminator's goal is to distinguish between real and fake, and they learn from the competition with each other. And at the end, fakes look real. So then the discriminator. So the discriminator is basically like a classifier. It takes in as an input as an image, and it gives. So it just tells you in a traditional GAN, it will just give you 0 or 1. So 0 if the image is fake, 1 if the image is real, and so this is what the discriminator will do: distinguish between different classes, like different classes, or in our case real and fake are also different classes. So and it's also a neural network, it's a CNN, or you can use it, or you can use a simple deep neural network as well. So you can see that these features that are input to the discriminator, they are coming from the output of the generator, and also the original training data set is being passed to the discriminator. So the output, all the output of the, in the initial step, all the output of the generator is labeled as 0, and all the original data set is labeled as 1, and that uh, as a supervised learning problem is passed to the discriminator. So yeah, so the discriminator is a classifier, learns the probability of class Y given features X, and the probabilities are the feedback for the generator. Now, what is the generator? How does it improve performance? Generator in terms of probability. So generator generates examples for the of the class. So you just pass in a number, maybe a random number, and generator will generate an image. So this is a pure GAN. Okay, so we will talk about some things known as conditional GANs. So you just give some noise, and then generator will generate this image. And okay, so this whole thing together is looks like this. So you have some noise, and you are trying to train these parameters. Generator will generate some images. That image gets passed to the discriminator. It generates an output. That output, the discriminator now sees whether it is true or false, whether it is fake or real, and it basically passes it on to the back to the generator. So in this process, the generator and discriminator weights get updated, and both are improving. But after a point of time, the generator outsmarts the discriminator, and that is the point when our GAN learns. So yeah. So the generator produces fake data, learns the probability of features X. The generator takes as input noise, so which are the random features, and then the what is the loss function that is used? So binary cross entropy loss equation. How does it look? So this I think we have already seen in the past when we have gone through all the material of deep learning specialization. I'll skip this. So now putting it all together, how does the whole architecture look like and how to train GANs? So you have a noise, so you have some random number generator, which gives a number to the generator. Generator generates fakes. So these are X hat are fakes. So these are labeled as zeros. And you have real images X, which are labeled as one. So this is with X and X hat and their labels. That is input as input to the discriminator. And now the discriminator learns how to distinguish between the fake and the reals. And so the task of the generator is to make the fakes which look like reals, which are actually not reals, but they look like reals. And so in the first step, so you have to train the generator. So okay, yeah. So this week got over here. So yeah, we'll see the week 2. And they talk about activation. So we have seen all these things. Common activation functions are relu, leaky relu, sigmoid, tanh. Yeah, we have seen batch normalization. So batch normalization is
Sir,
then yeah.
sir, I have some queries related to this topic that as you started. Uh, can I ask them? Hello.
Uh, Maybe can you keep it for later? I'll just finish GANs and then maybe you can post it in the chat so that you don't forget, and
Yeah.
we'll discuss.
Yes, sir.
Okay,
Okay. Okay, sir.
thanks. So we have seen batch normalization. So batch normalization is normalizing within the layers uh, of the deep neural network. And okay, so that was about batch normalization. GANs again. Yeah. So then they are introducing convolutions. So we have also seen convolutions. I'm skipping this. What is a padding? What is a stride? If you guys have any questions just on these basic things, just type in the chat. We'll discuss it later. Pooling and upsampling. We have seen pooling. So this is max pooling. And we also have seen upsampling, right? So upsampling is if you have a 2x2 input and you want to generate a 4x4 output. So this is basically what is upsampling. And then we have something known as transposed convolutions. So in a transposed convolution, you have the input is smaller, the output is bigger, and what you have is something like this. So if you have this filter, so input is 1402, filter is 2211. So you will say 1 into 2, and then this. So if you want to generate from 2x2 to 3x3, so then you will say 1 into 2 plus 4 into 2, and then this one will be 4 into 2. So this will be, so then in the middle it will be so 1 into 1 plus 0 into 2, and then 1 into 1 plus 4 into 1 plus 0 into 2 plus 2 into 2. So yeah. Okay, so there is a problem of checkerboard pattern with the transposed convolutions. There are methods to get away with this checkerboard pattern. You can go through this in detail. And then they're talking about mode collapse, and where is GAN then? Okay, I think it is there in the course 2 and course 3 of this specialization, which we will cover later. Okay, yeah, week 4 has some material on GAN. So conditional generation. So what we have discussed until now is unconditional GANs, in which we just pass an some random number as input, and it just generator generates an image, and discriminator then tries to identify it as a real or fake. Now we'll talk about conditional GAN. So in conditional GAN, what we have is it's not like we are just passing, giving a random number as an input. We are giving it a task, which is something like supervised. It is not completely generative. So maybe you can call it as a self-supervised learning also. So you give it some kind of labeled data sets. So training data set needs to be labeled, and why this is useful is we will see. So let's say if you have to tell the generator what type of example to produce. For example, in the super resolution problem, if you want to improve the resolution, so that is GAN is known as SR GAN. Now in SR GAN, SR GAN is a type of conditional GAN. It's not an unconditional GAN, because you have an input and you have a label. You have a low resolution input and you have the original high resolution target. So that is a conditional GAN. It's not an unconditional GAN. And so in an unconditional GAN, you have a noise vector, and then you basically do these things. Uh, okay. Yeah, these are the same thing. So the discriminator remains the same. And so the class is passed to the generator as one hot vector. The class is passed to the discriminator as one hot matrices. Like too many slides for very less concepts. Okay, fine. Okay, so guys, yeah, we have briefly covered GANs, and then I wanted to cover these models which are known as autoregressive generative models and made models. So this is mask autoencoder for distribution estimation. So in made, what you basically have is so you have an input and you have outputs, but in this case, the kind of input and output you can have is something like this. Okay, so only so this the output of the first output, let's say, is the probability of x1. Now this one, the second output is uh, like we say that it is only conditional to the first input. So the probability of x2 is conditional to only x1. So this one, the network is connected in such a way that it is only connected to x1. And yeah, in this case they are not showing it this that way, but yeah, I think the connections will be switched off in that case, when we have this kind of masked autoencoder for distribution estimation. So this model actually performs really well for a number of tasks. And then for the probability of x3, we find as conditional to x2 and x1. So the connections to x3 and x4 are turned off, because this is only conditional to x2 and x1, and the probability of x4 is conditional to x3, x2 and x1. So this is its connection to x4, like this one, it will be turned off. So that is the made model, which you can go and see the details later on. And then we have something known as pixel RNNs and pixel CNNs. So these are models which are known as autoregressive models, and they are different from GANs in a way that GANs learn implicit data distribution. So in GANs, you later on it's just generating some data, right? It is not something which you have basically taught to the model, or you have made as a label data set. Whereas in autoregressive models like pixel RNN and pixel CNN, you have an explicit data distribution governed by a prior imposed by model structure. So that is the primary difference between GANs and pixel RNN and pixel CNN. Pixel RNNs, you can see the model's performance is actually really good. It's comparable to GANs as well. And then there are different architectures in pixel CNNs like gated pixel CNN, pixel CNN plus plus. So yeah, I just wanted to introduce these models, and then there was a hands-on that I had planned. 3:25. I am tired. I will do this in the next class. So from next week we are meeting every day, and